for the reason today I will do slowly. And so far we have dealt with the real vector space, and we want to generalize that to more general vector space, and then we might need what is vector space, and we will generalize from real vector space and space. So it is definition, and maybe it will be called it axiom of vector space. First, I will denote him here. Firstly, we in real vector space we define the addition and scalar multiplication. So first, we might need what is addition. So to define addition, we will define will be a set, and finally we will call it is vector space as two elements in the set V if it satisfied for an operation plus another one. We will define plus, so maybe we want to, it is in V. Sometimes we skip this notation by defining the additional operation is binary operation, and binary operation means it is closed in that set. However, in our book we denote as a first axiom of vector space, and the second, it is commutative because we want to like really additional operation, and additional operation has commutativity, and also it has associativity. I will denote the property of addition, and also we defined the real space when we define real space we made the zero sequence, and it can be by defining that we define subtraction also, and so to make subtraction we are needed 0 in that set V. In my note I misnoted it is U, and also U plus 0 equal also U. And I say that by defining 0 we can define the subtraction. So I will the subtraction, the minus U can be get like subtracting, and if V has these elements, then we said this is additive plus for that operator. And also we defined the scalar multiplication. So for that, firstly we will write we worked in number set, real number R. However, it is okay to choose another number set, or it is also in vector space. You might know some number set. It is where it's good number set, like rational number or complex number. It is very good number set because if you take an element in here, then the 1 over the elementary is also in that set if A is not 0. This set will be called it field, and so for a field, we can define the scalar multiplication to the vectors to the set V. So I will write field as F. To be a field like real number or complex number or rational number. In our case, in real vector space case, we define it as a real number, and the scalar multiplication means the in coordinate system in n real space, it was just multiplied to each vectors, and we will define it similarly or work similarly, and it is necessary in for the result of scalar multiplication is in the set V. It is also sometimes submit by defining the scalar multiplication is binary function. In this case, we need to one scalar and one vector. It is sometimes called it a binary function. And for that function scalar multiplication, it has distribute row and also the scalar can be distributed K and M. K scalar multiplication U plus M scalar multiplication U. There is also distributive rule. And also it has associative rule. That means K times M scalar multiplication to U is equal to K scalar multiplication M scalar multiplication U. We will work having associativity. It will give a convenient calculation in vector space case. And finally, as like we defined 0. In the field case, it has similar element of 0. It was 1, and it will not change the any element of V. So if V satisfies these 10 axiom, then we will say V is a vector space over F, over a field F. So as to check it, the set of V is the set of V vector space, then I think it is. There are too many axioms. However, it will be divided into 2 parts. One is additive parts, and another one is scalar multiplication part. So by checking commutativity, by checking associativity and 0 and distributivity, we can check that is vector space or not. Let me give an example. We firstly see the R space, N space. I explained we generalized from R space, N real space. So let me see. I will skip over. For an element UV, if the additive operation is defined as just really for that additive, U2 UN plus V1 V2 Vn. We defined it as the addition of each vectors. I mean U1 V1, U2 V2, UN Vn, and also we defined the scalar multiplication. K. Scalar multiplication by K is U1, U2, and defined it multiply 2 for each vector. Then firstly, we can see it is in that vector space easily. I mean, the closure property has satisfied it for the operation, and also the additional the addition in the number space R, it has the commutativity and associativity, and also we defined it for each vector by the scalar multiplication. So if you consider for each vector, then it will satisfy the distributive rule and the associativity by the scalar multiplication. So if you define the operation like that, then it will be a vector space. Also, maybe there are another case also. We defined it until the finite number n, the dimension of finite number n, and it, when you consider the any sequence in R real number, like if the vector in U in V is defined as a sequence, then in this case also we will calculate in for each vector, and we can check the space V satisfied is satisfied these axioms of vector space. So in this case, also V is also a vector space. And so far we see some space like metric space and polynomial space. That is all a vector space, and vector space quite weak condition in my opinion, because although there are 10 axioms, it is just for additive rule and scalar multiplicative rule. So it is quite weak condition, and so there are many vector space. Okay, if I define V is a 2x2 matrix, all the collection of all 2x2 matrix, then it will be also vector space. So 2 times 2 matrices, and if you define the additive operation like U11, U12, U21, U22, this also can be see the dimension 4 your vector space. V11, V12, V21, V22, U11, V11, V12, V12. If it will be defined the addition of matrix as addition for each vectors, and we define the scalar multiplication to the matrix U as for each vector K is in real number. It will multiply to each vector, and so in this sense, in vector space sense, we might not be able to divide the space R to the 4 and divide all elements in 2x2 matrix, because by denoting these elements, that element U as a sequence with length 4, and then the addition and scalar multiplication is same to the above definition. In vector space, the two things is same. However, we defined the multiplication in matrix space. So, like in this case, U times V was it satisfied the column row column property. U12, V21, we have two vectors, and it is in 2 by 2 matrix also. However, we do not define this multiplication in the space R to the n. And also, I will see another example for function, because the function that is also a vector space, and I want to divide the set function. I will erase this page. So the axiom of vector space means it has additive operation and scalar multiplication operation. And actually, when you consider the function, function plus function will, if it has same domain, if it has same domain, then it will have it might be able to edit and scalar multiplication. I mean, let V be the set of real valued functions. And the additional operation works for each addition f x plus gx. And when we define the scalar multiplication of f as the result of f, the real valued function means if you have a domain D, then f and g it goes to in the real number R. So if you define like this, then actually it will calculate it in for each function it will calculate it in the codomain real number, and the additional operation and scalar multiplication is just additional operation in real world and multiplication in real world. So it satisfied all axiom of vector space. And so for that reason, the set of V is also a vector space, and it is denoted is F over D, and now I will write D is an interval from minus infinity to infinity. Then we denote it is f of minus infinity to infinity. So we might think the function space f minus infinity is a vector space, and also we might know another function space like continuous function or differentiable function. In that sense, I denote in the layer of my material, or I will give one more example. Okay. Let we be the set of continuous real valued function in the real analysis class. You might learn that the continuous function, edit continuous function is also continuous function, is closed. It is closed, and if you multiply on a scalar to the function, it is also closed, and so we might guess the continuous real valued function is also a vector space. And it is denoted C minus infinity to infinity, or C0 minus infinity to infinity. And this continuous real valued function is also real valued function. So it is the set C0 is a subset of F. If I denote it in as a graph, then it will that. And actually there are a special vector space. It is not defined like additionally and multiplicationally. I will give that example. I want to know what is vector space, and vector space how have weak condition. When you consider the positive number in the strictly larger than 0, and in that set, if you consider just real addition, we have used additional and scalar multiplication to here, then it might not be true, because it will not be vector space, because it does not have -1 minus k. However, if you define the addition to as a multiplication of the number in real number, and if you define the scalar multiplication to u to the k, then it is also closed. This operation is closed in larger than 0's real number, because if you multiply to positive number, then it will give positive number, and if you bring a scalar k in R, then it is also in that space. So it is closed in for each operation, binary operation, binary function, scalar multiplication. And also you might be able to check the commutativity of additional operation, because u times v is same to v times u, and also it has associative rule because u v times w is same u v times w. That means it is u plus v plus w, u plus v plus w in that operation plus. So in this sense, if you check the action of scalar multiplication also, then it will satisfy the distributive rule and the associative rule. And I think it is, you can check it easily. So I give an example of continuous real valued function is in the vector space F. It is just real valued function, and it has this subset property. And I want to say this will be called the subspace as a vector space. Almost everything is has satisfied the vector space axiom, so usually we say it's just subspace. And then I think I have to give what is subspace. So let me be a vector space. I do not. And let W is a subset of V, and also I will write to coordinate W to be vector space of V, or subspace of V. It should satisfy the vector space axiom. Then just if W is subset of V and it is also vector space, then W is sub-vector space of V. In this case, C, the continuous valued real valued space C0 is the subspace of just real valued function space. That is an example. And I defined it, it should be satisfied with all action of vector space. However, there are too many checklists, 1 to 10. There are 10 axioms in vector space axiom. However, if I will use I will check W. If the elements U and V in W as a subset of V, and W satisfied the closure property of over additional operation, and also for a scalar k, it is the scalar, the number set of V. I will denote F. Okay. And U is in V. If W satisfies this second property, the scalar multiplication is closed in W. Then in this case, actually when I explain the axiom of vector space, it sometimes skipped the closure property by giving it is binary operation, and another operation is really axiom. It has commutativity and additive, associativity, distributivity. This property is satisfied in the space vector, the vector space V. So actually, it is okay to check only the closure property in vector space in the set of W. So if W satisfies this property, then W is subspace of V. I think if you get this property, its proof is also just by using the operation defined in vector space V. You can check the additivity and commutativity, distributivity, associativity for each operation plus and scalar multiplication. And actually, I already proved it in real space in the previous chapter. So let me give more subspace in the real valued functions at F. We checked that C0 is a subspace in F, and also let C1 be the set of differentiable real valued functions. Then we can check the closure property in the space C1. Since for two differentiable real valued function in C1, when we calculate the addition for each function f and g is also differentiable. That means it is in this space, and also for any scalar k, k in scalar r, then the k multiply f, k multiplying f is also in the space of differentiable. So for that means it has closure property, and by the theorem the space C1 is the subspace of the real valued function f. And also we know that it is the differential map satisfies the continuousness So that means it is also a subspace of C0. And similarly, that means it is if you derivate, if you do one derivate, then it is, and also it is continuous, then it is in this space, and then you might think if you derivate n times, then it is also can be vector space in the same sense, and then it is a subvector space of C1 and subvector space of the function space F. And also we can, when we give an example of C infinite, C infinite means you can derivate as you want, as much as you want, then it will be called C infinite. Then in this function, you might get polynomials can be divided, can be derivated for infinite times, because if fx was x squared, then f1 is 2x and f2 prime is 2, and f n times derivate, then it is 0 for larger than 2. Yeah, this differential. Yeah, it is differential per function for you when you how many. It does not depend on how many do differentiate to the function. Yeah, zero function is also real valued function, and this function is also differential function. So for that reason, we will call the space polynomial will be denoted P for that domain minus infinity to infinity. Be the set of all polynomials on minus infinity to infinity. Then, of course, polynomial has closure property in addition operation and scalar multiplication operation. So that means the polynomial space is also a subspace of the real valued function set, and it has subset property with C infinity. So it is also a subspace of C infinity. And also when you consider the limited degree of polynomial, that means if the degree is less than or equal to d, then we will denote it is p sub d, like that, with a set of polynomial on minus infinity to infinity of degree less than or equal to d. Then it's addition, if you edit the degree d polynomial, then it will be degree d polynomial. and so it has closure property also. So in this sense, this degree D polynomial is also a subspace in the space polynomial space. And actually, any linear map means if I will L is linear map, then A plus I will use the vector U plus KV is equal to LU plus KLV. If it satisfies this property, then we say that is linear function. And when you consider the degree only homogeneous degree 1 polynomial, it satisfies this property because we are considering the domain minus infinity to infinity. Then when you consider for a two number in minus infinity, and the scalar k, actually that is all same. For that case, when you consider the let me give an example. If L is just a one variable, I will use two variable function, and it is x1 plus x2. Then when you input the elements, I will use only one variable because I use the A and B, and then we should check A plus KB equal L of A plus K L of B, and I will define Lx just X as a linear map. If you define that, then it is a linear map, and it is just A plus KB, and A is L of A and B is L of B. So for if you bring for any homogeneous degree 1 polynomial, then it will divide, it has, for each vector will have linearity, and so in that sense, if you gather a linear function in that, in this case, really the linear space is also a vector space. A linear real valued function is also linear space. However, I think it's not interesting that because there is two small elements. And I explained it the set of I explained that the set of all matrix is also a vector space. However, we see some property in matrix like invertible matrix. For the matrix multiplication, invertible matrix has closure property, and also upper triangular or diagonal matrix case also satisfy the closure property. For that case, if you define the additive operation as the matrix multiplication, and scalar multiplication is really scalar multiplication, then it will be vector space, sub-vector space of matrix multiplication vector space. I will give property of subspace of V. If you have R subspace of V, V is a vector space, then the intersection for each subvector space is also subvector space, subspace of V, because it will satisfy the closure property for each vector. And so if you calculate only the elements in the intersection points, then it will satisfy this closure property. So by the following theorem, you can check it will be subspace of V. However, then you might think that when you consider the union of subspace, in this case, in general, it is not subspace of V. That means U1, union U2, union UR is not a vector space, subvector space of V in general. For example, I think it is more very formal example. When you consider a subspace in R2D2 space, one is the axis of X. Then it in the vector space R2D2, we give the additional operation as edit for each vector, and scalar multiplication is multiplied for each vector. So if you choose only first vector, and in this sense, the x-axis means its entry is alpha, 0, because the second vector is 0. So it will be closed. It will be closed under the addition operation and scalar multiplication operation. So it is a subspace of V of R2D2. And when you consider the y-axis, it is also a subspace of V. However, when you consider the union of two subvector space W1 and W2, then it is not a vector space, because when you add it for this vector and this vector, then as a parallel rule, it will give this vector. However, it is not in W1 and W2. So the union does not give a subvector space in general. And this theorem, the following theorem is will connect the linear system and vector space. And I explained it, the why homogeneous polynomials needed That is, it will give a vector space, sub-vector space in the space. When you consider the homogeneous system of n equations and n variables, I mean n unknowns, then its solution set is also the solution set is a subspace of an unknown, then r to the n. It is to check it is a subspace in r to the n. We should check whether it has closure property under the two operation. However, when you consider the to each property to have this property that x0 and x1 be a solution, be solutions of the system, then we can get x0 plus x1 is also satisfied with 0. So for that reason, it has closure property in addition, and also when you consider the real number k and for the scalar multiplication for k, k of x multiplied to a is same to k a sub x a x of 0, and it is same 0. So in this case also satisfied with the closure property for under the scalar multiplication operation. So we get that the solution set is a subspace of R to the n. However, when you bring the non-homogeneous system, that it will not give a subspace, because the vector space should have the 0 vector, and in this sense, if you give a non-homogeneous polynomial, then 0, 0, 0, 0 will not be a solution, then that means it will not be a vector space. Next. I think I skipped the number. I'm doing this one. in my note, I'm doing subspace. I noted that. I noted it in here, however, I erased it. What time is it now? Maybe you have class at sorry. I think today's class you learned in your class in this semester. Right, yeah. Maybe it's okay to skip today's class. The next. This is just for matrix transformation. So let T sub A be a linear transformation, that is matrix transformation. I want to say the set of solution for that in the domain. I mean, notion of A. Then the space, we might be able to consider the space, the set of solution. Solution means when we find the set of, when we go to X, if it become a 0 in the codomain R to the M, then from the previous theorem, it will give the set of solution. And so it will be a vector subvector space in R to the N, and it will, that means it has a speciality. It is the special set for the linear transformation T sub A. So it is called the kernel of the matrix transformation T sub A. And this kernel is quite useful object, and so I want to focus on that. As I say this, the next theorem means for any matrix transformation, T sub A, the kernel is a subspace of the domain space. When the domain space vector space, in transformation case, the domain and codomain space is R to the N to R to the M, and this is a vector space, and codomain is also vector space. So in this case, the domain space is vector space. And now we can focus on the topic of linear combination. I explained the linear combination means it is it has closure property for addition and multiplication. And so when we learn the subspace, we might have some questions. What is smallest subspace, and what if you give a subset of V, then what is the smallest subspace including the subset S of V? So in this sense, in this section, I will answer the question. Of course, just if you consider the smallest set, then you might consider the zero space. It has only zero vector. Then it will satisfy if you give any binary operation, addition operation, and scalar multiplication operation. So it will be called a trivial vector space, and it is not our interest. And then for the second question, when we give a subset S of vector space V, what is the smallest vector space having S? And to answer for the question, we need the concept of linear combination. Actually, I used it in previous chapter, and to give a theorem of the subspace, I will recall one more. Let small w be a vector in a vector space V. The small w is called linear combination. If it has the form linear combination of V1 to VR, of V1 to VR, and for each V I is in V vector space V. And so if it has the form C1 V1, C2 V2, CR VR, here the CI's are in base field, and I will denote base field with slash. If W has this form, then it is called a linear combination. And why we need this? If you ask why we need this definition, then the next theorem can answer for your question. If S is a subset of vector space V, I said the zero space is not interest, so I will say it is non-empty subset in S. And then we might consider the linear combination by W1 to WR, and we will construct a set of the linear combinations or possible combination of S of vector in X. Is a subspace of what our whole space set in V, and V is a vector space. So W is a subspace of V. And the second property is said thus that W is the smallest subvector space of V containing S. I will prove it. To check the subspace, I said it is enough to check it has closure property for each operator, addition operator and scalar multiplication operator. So to check it, if you bring two elements of linear combinations in W, then and I will say it is, I will denote that is U and V. That means U is C1 W1 plus C2 W2 CR WR, and V is D1 W1 D2 W2 DR WR. So in this sense, we defined the additive of two vectors in vector space V by when the direction is the same, it is satisfied the associative distributive rule. That means it is saying C2 D2 W2 CR DR WR, and so it has closure property over additive operation, and also for each scalar K scalar multiplication to U is just KC1 W1 KC2 W2 KCR WR, so it is also satisfied the closure property. So we can check that W is subspace of V, and also we are considering it is the smallest subspace of V. If you assume that W is not smallest subspace, then we can have a proper subspace W prime subspace of V such that it is smaller than W, then it's W prime is also a set of the vectors in W prime will be denoted like this form because it is smaller than W, and so it should contains or element of W. However, let that is containing and it contains S, and so it also had closure property to be a subspace. And so for this sense, if you bring an element U prime, V prime in W prime, then when you collect all elements of linear combination of U and V in that space, W prime, then it will be W. I mean, when we collect all linear combination in or vector I will say in W prime, then it should contain the set of W by the definition of W, because we gathered that W is the linear combination of S, all elements of possible linear combination, and when we find a linear combination in W prime, then it also contains the set of S, and so that means the set of all linear combination of W prime, if we denote it is, then I think it is a spoiler. It contains W because it was a set of linear span of S. It is a collection of all linear combinations by constructing from S, and it is the space by constructing from W prime. And W prime since W prime contains S, it should be larger than or equal to W. However, we know that from our assumption, W prime is proper subset of W, so it is contradiction. And so W is the smallest subspace of V containing S. I said the span of that set. That means the spanning set means really expanded by the set S or W prime satisfying the smallest vector space containing S or double prime. As a remark, this, I erased that. The space W we discussed so far is called the subspace of V expanded by S, and we denote it is denoted by span of S, or span the set of S, W1, W2, WR. Sometimes we denote having bracket, circle bracket, or this bracket. It is just notation. If you want to use anything you want, there's one you want, then it is okay to use that. I think it is not good notation because set S is set, and so sometimes it might give confused the set of set. So I think it is better to use just bracket or circle bracket or just S. Then what is the spanning set? If you have the question for that, and so I will give some example. We considered the standard basis in previous chapter, and actually the next chapter of spanning set we will learn what is basis. However, actually I spoiled for that, so I bring this example. So the standard unit vectors was E1 1,0,0. E2 is 0,1,0. En is 0,0,1. This vector set is called the standard basis. And why it is called the standard basis is it will span the set of it will span the vector space R to the n. Actually, we discussed for that. For every element V in the space R to the n, it will be denoted V1, V2, Vn. And then we can be denoted V1 scalar multiplication E1 plus V2 scalar multiplication E2. Like that we can denote Vn En. So it is the linear combination form of the set of standard basis S. And so From this, we can check that the space R to the n is same to the space expanded by S. Actually, I bring the example polynomial PD, and in this case also we might make the spanning set. Everything underline. If you bring the set S as 1x x squared x to the d, then it will span all elements of less than or equal to the degree less than or equal to d. So that means span of S is same to the space of d polynomials in over R. I will just pierce up D. I will use the base field R. Maybe today I think there are too many examples instead of proof, because we learned the axiom of vector space. Is better? I think so too. It is easy to convey for that. Not easy to understand to students. And then then I will explain until the final theorem. It is the final theorem of the chapter section 4.3. Did you have a lunch? Maybe you had also class before this class. Do you have any plan? You have breakfast. You did. And do you have your lunch meal in our laboratory? If you don't have that, I expected to suggest to have together. If you okay. I didn't have yet. Yeah, if you can. No, I don't have bento. So. Yes. Then time is up a little bit. Okay. I'm thinking to skip my lunch also. That is impossible. You don't want to. Yeah. Yeah. are really like Ramadan. Is different from Ramadan. Uh, uh, okay. I'm uh, I'm thinking how I clear my lunch. How I take my lunch. Okay, let's back to our class or lesson. And if you have back, two set of a vector space V, and its expanded set is same, then it has Bernoulli property. It's each vectors in S can be written as a form of linear combination of the vectors in S prime, and also if respectively not respectively, and also is satisfied that its vectors in S prime can be written as a form of linear combination of the vectors in S. Also, I want to say the uniqueness. However, in this section, we will not say the uniqueness because and actually it is a little different from uniqueness because it can be written as the form of linear combination of the form of form, and so actually the set of S and the set of S prime not equal, although it can span same space. Let me give one simple example. When you consider R to the 2 space, if you bring two vector E1 and E2, it is 1, 0, it is 0.1. And when you consider the spanning set of by two vectors, then it will span the whole plane. And actually, if you bring another vectors, E1 and E2 prime, it is 1, 1. Then by making E2 prime minus E1, by calculating this, we can make E2. And so this theorem says the spanning set of E1, E2 is same the spanning set by E1, E2 prime, because E1 can be written as a E2 can be written as a linear combination form of E1 and E2 prime, and conversely E2 prime can be written E1 plus E2. So if you believe this theorem, then the spanning set is same. So it is said just spanning. If you have spanning vector space, then you can find like basis, we will say that is basis, and the number of bases is not unique. We can choose several bases. So it is a little different from the uniqueness. However, you might say the uniqueness of standard basis. What is standard? Then you might get what is the most standard basis, and it should be unique. To say it is standard unique vector or standard basis. As a proof, it is quite easier. If you use the previous theorem I wrote here, that theorem says the expanded set means the smallest set containing the set, and so from that fact, the expanded set by S is the smallest subvector space. Of V containing S, and actually this space containing S prime, so we might consider it is this inequality, and also we get that inequality span S prime, because span S prime is the smallest vector space containing S prime. I will explain again. The spanning set S is the smallest subvector space of V containing S, and also since it contains S prime, so it is smaller than S prime, and analogously, if you bring the spanning set by S prime, then it is contained the set S from I'm considering the right side. If that means each vectors in S can be written a form of linear combination, means the spanning set contains the spanning set by S contains S prime as a linear combination form, and when you consider the space by expanded by S prime contains S as the linear combination form, so we have this subsequence subset property, and this set is the smallest set of containing S, so we have this inequality, and similarly we will get that inequality, that subset property, because S prime is I think it is better, right? Since span S has the smallest subvector space containing S, and S prime also has the set of S, we have the subspace inequality, subspace property, because it's the smallest. And similarly, since the expanded by S contains S prime from our assumption. So it contains the smallest subspace spanned by S prime. For that reason, we get that span S is same to span S prime. And conversely, if two vector spaces same means actually for each vectors is also in the space expanded space, and then that means this element can be written from a form of from this space of linear combination. And conversely, if you bring the elements in here, then it will be denoted as a linear combination of this space. So that means it is also clear. Okay, I will done here.